could do for these systems can kind of intimidate people with the problem, because there's like a billion things you could do. You only need to do like simple steps to find the solution that you want, but it's not always straightforward. And it's also not very systematic. So this is one of the things about this class that I think is challenging, is that we learn a bunch of different things about a bunch of different types of measurement systems. But to find the solution to any given problem, there's no systematic method. Like I don't give you guys, like in mechatronics, I give you guys like steps, like 1, 2, 3, 4, 5, 6, and analyze the circuit in this way. This class doesn't lend itself to that sort of a method. So it's sort of like learn a lot of different things about measurement systems and then apply them to different types of problems. So I think this class it's a challenging class, I think, to keep things straight as far as, I think that's why it'd be difficult to study for an exam too. Because you just never really know what is going to be asked, because you can ask, on the quizzes, like I try not to get too creative, because they're like, even the problems that you guys do, I could ask so many different types of questions about the problems that you guys do. So, yeah. The main takeaway though from all of this is to get a feel for how measurement systems work, how to use them, and then how to analyze them so that you can use them well. So that's the goal here. And I think that you guys might not be able to see it because we do have to wade through quite a bit of theory for a while, but then we're going to get to a point where it's not too bad. Promise. So, properties of linear time-invariant systems. We have thus far dealt with first order and second order and zeroth order dynamic systems, measurement systems that respond to inputs. But we've also dealt with some that are in free response, just to initial conditions, and others that are forced with some input, right? We've dealt with all of those things, but we've always dealt with them separately, right? Either there's an input or there's an initial condition. There might be an input and initial condition together sometimes, and there also might be multiple inputs. That's what this lecture is going to allow you to do, is glue those together. You have it all, you just need to be able to glue it together. So from the principle of superposition, linear time-invariant systems, which means that the parameters in the system, like the mass and the spring constant and the capacitance, they don't change. Time-invariant means they don't change with time. So these systems they respond to both initial conditions and non-zero forcing. And so the solution, when you have both, can be obtained by summing the free and the forced response. So we developed some free response solutions. We developed some forced response solutions. Turns out that if you have both free and if you have initial conditions and you have forcing, all you need to do is just add the two together. So that's pretty nice. And what's really convenient about it is that it allows you to analyze a system once for free response, once for forced response for a given input, and then if you ever have some combination of those, you can just slap them together and you're good. You don't have to worry about redoing the whole problem. And that's part of why I can give you these. I can give you the free and the forced response solutions in the chat and the previous lectures, and you can be able to use them and apply them elsewhere. So moreover, superposition says that any linear combination of inputs yields a corresponding linear combination of outputs. That is, we can find the response of a system to each input separately, then linearly combine by scaling and summing the results according to the original linear combination. That is, so in math language, for inputs u1 and u2, constants a1 and a2, a forcing function that includes a linear combination of u1 and u2 will yield an output that's just the same linear combination of the output of the system to u1 and the output of the system corresponding to u2. So you can essentially, if you multiply the input by something, you can multiply the output by something, and that would be the same result. If you add two inputs, same as adding the two outputs. This is true of linear systems, which make them really nice to work with. So think of this as like U1 made U2, or U1 made Y1, U2 made Y2, and if you want to find out what happens to the system if you put in these together, combined with these scalars that are scaling them, it's literally just like the easiest possible answer, which is you just scale and sum the outputs. It's nice. So you can find the system response to U1 separately, U2 separately, and then you can find the total response by just summing them up. All right, so this powerful principle allows us to construct solutions to complex forcing functions by decomposing the problem. It also allows us to make extensive use of existing solutions to common inputs. There's one more, so the two that I developed were for step input and for the sinusoidal input in this chapter. There's one more linear time-invariant system property worth noting here. Let a system have input U1 and corresponding output Y1. If the system is then given input U2, which is the time derivative of the first input, U1, the corresponding output is just the time derivative of the output of Y1. So whatever you do to the input, essentially you do the same thing to the output, and you don't have to resolve the problem. And that works for scaling, summing, taking the derivative. It also works for the integration. I didn't say that. This is also true for integration. So, great. So now we're set up for the last sort of big topic in this chapter, which is when we have periodic inputs that are not just sinusoids. And we're going to use Fourier series again for that. And superposition. It's going to be so badass. You will be so happy when you get to see how you can do that. It's so much fun. Okay, so Wednesday, look forward to that.